Okay, so moving up in our carboxylic acid derivatives, we have the nitriles, which actually don't contain a carbonyl carbon, but exhibit similar properties to warrant its place with them. Nitriles are carbons triple bonded to nitrogen. They are also known as cyano compounds containing the cyano group. They are also terminal functional groups, and so we may encounter the same naming complexities as aldehydes. So let's name them. Okay, for nitriles, they are named almost exactly like aldehydes. For linear nitriles, we use the suffix nitrile. Then we find the longest chain containing this nitrile. Here we have 4 carbons. So we have butane nitrile. Here we find a substituent ketone denoted by the prefix oxo. And then we do locant numbering, 1, 2, 3, and 4. So assembling the name, we get 3-oxo-butane nitrile. Again, no number indicating where the nitrile is located because it is a terminal functional group. Like aldehydes, we can encounter the same complex situation for nitriles connected to a cyclic parent chain, as the nitrile group is a terminal functional group. In this case, we use the suffix carbonitrile. Attached to the parent chain, we find cyclopentane carbonitrile, having a methyl group here, and performing locant numbering, setting number 1 at the carbon alpha to the carbonitrile, we get 2-methyl cyclopentane carbonitrile. Nitriles, when named as substituents, use the prefix cyano. Okay? Note that the cyano carbon is also included in the substituent name and must not be part of the parent chain. So this carbon, okay, whether linear or cyclic, this carbon in the cyano substituent is not part of the parent chain. Here's the monosubstituted benzene nitrile with the name benzonitrile. This cannot be used. This can be used with substitution. So here, for example, we have 4-amino 2-trifluoromethyl benzonitrile. Nitriles, being terminal functional groups, also apply the same common naming schemes as aldehydes. In this case, we use the suffix nitrile. So, common prefix plus nitrile. Aceto plus nitrile, and alpha-methyl propion nitrile. Alternatively, we may also refer to the alkyl group connected to the cyanocarbon, adding a second word, cyanide. Okay, because the cyanide group is this CN group. So for example, we have a methyl group. Connected to this group, we have methyl cyanide. Cyclohexyl, 6-membered carbon ring, cyanide. Or isopropyl cyanide. Let's work on some examples. Here we have 2 carbons, 1 and 2. Ethane. Okay. And then we have the nitrile group, nitrile. So when we assemble the name, we have ethane nitrile. Okay, let's check. Ethane nitrile. Okay. Let's go to the next one. Here we have our nitrile group. Okay, and then counting the number of carbons, 1, 2, 3, we have propane nitrile. Okay, and then we have a substituent. Okay, here. So we have an amino group, and connected to that amino group we have methyl. Okay, and this belongs to a complex substituent, methylamino, 1 carbon. Okay, and so when we assemble the name, we have to add locant numbering 1, 2, and 3. So again, since it's linear, this carbon is part of the parent chain. So 1, 2, and 3. So when we assemble the name, we get 3 methylamino propane nitrile. Okay, confirming 3 methylamino propane nitrile. Okay, let's go to the next. Here we have another nitrile. However, this nitrile is its cyanocarbon is not part of this larger cyclic ring, but we need this to be our parent chain, which is cyclohexane. So we must use the prefix or the suffix carbonitrile. Okay, and so actually we just need to combine these two words to get cyclohexane carbonitrile. Okay, it exceeded, but here it is, cyclohexane carbonitrile. Okay, now for number 4. Okay, so here we have a nitrile directly connected to a benzene ring, and so we have a special name for that. We call it benzonitrile. Okay, and our substituent, we have an amino group here, so amino, and then connected to that we have an ethyl group, so we have ethyl amino, and close in parentheses. Performing locant numbering, set number 1 here always, and then number 2. So we have 2 ethyl amino benzonitrile. Okay, 2 ethyl amino benzonitrile. Okay, and for number 5, here we have nitriles, but there are 2 of them. Okay, 1, 2, 3, and so here we have a dinitrile, because we have 2. Okay, counting the carbons in the parent chain, we have 1, 2, 3, and 4. So we have butane dinitrile. Okay, and then we have 2 substituents. So we have a dimethyl and then Performing low-count numbering, we have 1, 2, 3, and 4. I could have started from the right, but in either case, it would be the same. So when I assemble the name, I get 2,3 dimethyl butane dinitrile. So we have two nitrile groups. 2,3 dimethyl butane dinitrile. Okay. And then for number 6, here we have a nitrile group. Let's find the longest chain. 1, 2, 3, 4, and 5. So we have a pent. Okay. And then at the end we have an alkyne, pentyne. Okay. And then we have a substituent, which is methyl. Okay. Now let's do locant numbering to get 1, 2, 3, 4, and 5. So if we assemble the name at position 3, we have our substituent 3 methyl. Okay. 3 methyl pent. And then we have an alkyne at position 4. Pent 4-ine. And then our parent functional group nitrile. Okay, 3 methyl pent 4-ine nitrile. There we go. So next we have amides, which are carbonyl compounds with an alpha nitrogen atom. So here we have the carbonyl carbon, and then it's connected directly to a nitrogen atom. And this nitrogen atom can be connected to hydrogens or other alkyl groups. So if they are connected to alkyl groups, we'll be using the same numbering method as amines and denoting that it's connected to the nitrogen. They are also terminal functional groups, and so will have the same set of complexities as nitriles and aldehydes. Let's name them. So amides are named almost exactly like aldehydes. For linear amides, we use the suffix amide. Okay, here's the amide. Then we find the longest chain containing this amide. Here we have 4 carbons. Okay, so we have butanamide. Note how I didn't include the this cyano group because it would it would still be 4 carbons. It would not be valid as the nitrogen connection has no official name. So this is butanamide. Okay, we find a substituent, cyano, right here. Okay, remember the cyano group has the triple bonded carbon to the nitrogen, and a substituent methyl at the end position of the amide. Now we do locant numbering, setting number 1 automatically to the amide group. Okay, so position 1 here at the carbonyl carbon. Assembling the name, we get 3-cyano N-methyl butanamide. Okay, it's ordered this way because of alphabetization. C before M. Okay, so simple. Here we have the same situation for amides as with aldehydes, in which we have a cyclic parent chain, and since amide is a terminal functional group, we have to use the suffix carboxamide. Okay, carboxamide. So here we have a carboxamide attached to the parent chain cyclopentane. So we have cyclopentane carboxamide having a methyl group in the ring and in the end position. And then we do low-cut numbering, setting it number 1 at the alpha position right here. Okay, and building the name, we get N2-dimethyl cyclopentane carboxamide. So if we have two methyl groups, even if one is in the nitrogen atom, we can combine them to make a dimethyl group. So N2-dimethyl cyclopentane carboxamide. Here's the monosubstituted benzene amide with the name benzamide. And this can be used with substitution, like so. Here we have 3,4-dichloro, so at position 3 and 4, okay, these are the carbons away from the alpha carbon here. We have 2-chloro, and then at position N, which is the nitrogen atom of our amide, we have a methyl group right here. So 3,4-dichloro and methyl benzamide. Being terminal functional groups, we also apply the same common naming schemes as aldehydes. In this case, we use the suffix amide. So if we have 1 carbon, we have formamide. Here we have a 5-carbon amide, common name being valeramide. Okay, and here we have a 3-carbon amide, so the common name would be propionamide. And having a methyl at the alpha position, we have alpha methyl propionamide. Okay, so we didn't discuss cyclic amides, but here's one significant utility of amides. So amides in nature exist, such as antibiotics. So here we have penicillin and amoxicillin, and they all possess the beta-lactam ring. Okay, so let's try some examples of amides. So here we have 2 carbons. Okay, we have our amide here. Okay, so we have an amide group, and then we have an ethane group. So when we assemble the name, we have ethanamide. Okay, so we have ethanamide. Okay, let's go to the next one. Here's our amide. And then we have 1, 2, and 3 carbons, so we have propanamide. Okay, and here we have 1, 2, and 3 carbons as our substituent, and so we have a propyl group. Propyl, and that's at the end position of our amide. This is the 1, 2, and 3 position. Okay, so when we assemble the name, we have N-propyl. Okay, N-propyl propanamide. Okay, let's see. N-propyl propanamide. Okay, number 3. Here we have our amide, but as you can see, it's connected to a cyclic parent chain. Okay, so we cannot simply use this as methanamide. Okay, what we can do is use the suffix carboxamide. Okay, and this is our cyclohex. Okay, and we have an alkene here. Okay, cyclohexene, and in consonant started vowel, and with vowel start with consonant. Cyclohexene carboxamide. And then when we do the numbering, we have position 1 at the alpha position, 2, and then 3, and so on. So we have cyclo hex 2 in, okay, no numbering, carboxamide. Okay, so cyclohex 2 in carboxamide. Okay, let's go to the next example. Here we have our amide directly connected to a benzene ring. Okay, so this benzene ring plus the amide would be benzamide. And so here we have at position N our alkyl substituents. We have two acyl groups, so we have a diacyl. And so when we form our name, we have NN diacyl benzamide. NN diacyl benzamide. Okay, let's go on to number 5. Okay, so here we have two amides. Okay, this one and this one. Okay, so we have a diamide. And then, when connecting these two together, we form the parent chain. So we have 1, 2, 3, and then 4, and then 5 carbons. So we have pentane diamide. And then we have here a substituent amino, and that's at position 1, 2. Okay, at position 2 of the parent chain. And so when we assemble the name, we get 2 amino pentane diamide. Okay, 2 amino pentane diamide. Okay, now let's go to the last example. Okay, here we have our amide okay, and this carbonyl carbon is part of a parent chain with 3, 1, 2, and 3 carbons. So we have a propanamide. Propanamide. Our substituents, we have here a methyl group at the end position, and we have here a complex substituent with 2 methyl groups connected to a nitrogen atom. So we have a amino group, and we have 2 methyl groups, so it's dimethyl amino, enclosed in parentheses. Now when we do locant numbering, we have N, 1, 2, and 3. And so when we assemble the name, we should get 2. Okay, at position 2 we have our dimethyl amino. close in parentheses. I started with this because we have letter D, okay, dimethylamino, followed by N-methyl propan amide. Okay, so it's 2-dimethylamino N-methyl propanamide. Next, we have acyl halides, which are carbonyl compounds with 1 alpha hydrogen or 1 alpha halogen atom. So that halogen atom may be fluorine, chlorine, bromine, or iodine. They are also terminal functional groups, and so we'll encounter the same naming complexities. So let's try naming them. Acyl halides are named almost exactly like aldehydes. For linear acyl halides, we use the suffix oyl halide, so that's OYL halide. So here we have an acyl chloride, okay, since we have a chlorine atom. And so the name of our longest chain containing 4 carbons is butanoyl, butan OYL chloride. Here we find the substituent methyl, and then doing locant numbering, starting number 1 at the carbonyl carbon, 1, 2, 3, 4. Okay, when we assemble the name, we get 3-methyl butanoyl chloride. In the same manner like aldehydes, if we have a cyclic parent chain, okay, we use the suffix carbonyl halide. Okay, in this case we have a carbonyl bromide attached to the parent chain cyclopentane. So we have cyclopentane, carbonyl bromide. Having a methyl group at the ring, when we do locant numbering, we set number 1 at the alpha carbon, and then number 2 for our substituent. Okay, assembling the name, we get 2-methyl cyclopentane carbonyl bromide. Here are the monosubstituted benzene acyl halides with the name benzoyl halides. Specifically, we have benzoyl fluoride, benzoyl chloride, benzoyl bromide, and benzoyl iodide. These can be used with substitution as long as you set number 1 at the alpha carbon. So it's this one. Being terminal functional groups, we can also use common naming prefixes for acyl halides, much like aldehydes. So what we do is we use the suffix -yl halide, so that would be 2 words. So here we have a 2-carbon acyl chloride, so we have acetyl, using acetyl chloride. Here we have a 5-carbon acyl fluoride, so we have valeryl, okay, valeryl fluoride. And here we have a 1-carbon acyl iodide, so we have formyl iodide. So that is those are common names of acyl halides. Okay, let's work through some examples of acyl halides. Okay, here we have 2 carbons, so we have an ethane. Okay, so again, we first identify our acyl halides. We have in oyl chloride. Okay, chloride because we have a chlorine atom. So we have our final name, ethanoyl chloride. Okay, so notice that when naming acyl halides, we use 2 words, ethanoyl chloride. Next, let's work through this example. Identify first where our acyl halide is. So we have here an acyl bromide, so we have oil bromide. We have here 1, 2, 3, 4, and 5. So we have a pentanoyl bromide. And then here we have 2 chlorines, so we have a dichloro, and here we have a fluoro. Okay, so in naming, dichloro will come first, and then after that is fluoro. We do locant numbering. We have 1, 2, 3, 4, and 5. And then we assemble the name. So here we have 3 dichloro, okay, followed by 2 fluoro, pentan oil bromide. Okay, so we have 3 dichloro, 2 fluoro, pentanoyl bromide. Okay. Now for number 3. Here we have our acyl halide or acyl fluoride. Okay. This carbonyl carbon is not part of a linear chain but directly connects to a cyclic chain. So we have to modify our suffix to use this as our parent chain. So we'll be using carbonyl fluoride. Okay. And then here we have cyclopentane having 5 carbons. Cyclopentane carbonyl fluoride. So okay. So we have cyclopentane carbonyl fluoride. Okay. Let's go to number 4. Here we have our acyl. Okay, we have a letter I, acyl iodide. This carbonyl carbon is connected to a benzene ring, and so we have a special name for that, benzoyl iodide. Okay, and then if we do locant numbering, set number 1 here, set number 2 here, we have a substituent iodo, okay, from acyl halides. So we have 2, at position 2 we have an iodo, position 2 of our benzoyl iodide. Okay, 2 iodobenzoyl iodide. Okay. Now for number 5. Here we have 2 acyl halides. So we have a dioyl. Okay, so it's linear, connected to a linear chain, so we can use dioyl. Okay, however, when we use the when we add the second name, which is the halide that our acyl halide is composed of, we also have to add a di to our halogen, so we have dichloride. Okay, so we have a dioyl dichloride. We have 4 carbons in this parent chain, 1, 2, 3, and 4. So we have a butane parent chain. So we have, as named, butane dioyl dichloride. So here, butane dioyl dichloride. Okay, so enclose it in a green box to emphasize that for 2 acyl halides, you have to also add a di prefix before the halide name, or the name of the halide. So chloride, dichloride. Okay. And for number 6, we have 2 acyl halides. Okay. That are connected, each of them directly connected to a benzene ring. Now in this case, we cannot use benzoyl chloride because we now have 2 of the parent functional groups. So benzoyl chloride or benzoyl halides are only applicable to monoacyl halides, monoacyl benzene halides. But for this case, we will have to use our carbonyl halides. So here we have carbonyl chloride. But since we have 2 of them, we have to use dicarbonyl dichloride. Okay. And then our parent chain is benzene. Okay. And when we do locant numbering, we have 1, 2, and 3. So when we assemble the name, we have benzene 1,3 dicarbonyl dichloride. Benzene 1,3 dicarbonyl dichloride.